In my talk today, I would like to present to you the results of our prototype testing of a new groyne design, which is optimized with respect to withstanding long-period shipwave loads. To illustrate how and why long-period shipwaves can be so destructive, we will watch a snippet of video showing the interaction of a primary shipwave with a groyne. We will see a wave generated by a post-Panmax vessel that is passing the groyne with a speed of 13 knots and a passing distance of just shy of 230 meters. The tidal water level is at approximately mean sea level. As we can see in the inset, the long period wave consists of a bow wave, a drawdown, and a stern wave. And as will be demonstrated in this video, it is in particular the action of the drawdown and the primary wave that can lead to high destabilizing loads on the rock armour. As indicated by the red bounding box, our video starts in the drawdown phase and shows the arrival of the stern wave. The action of the drawdown is creating a water level gradient, causing overflow over the groyne and flow around the groyne head against the direction of travel. As we approach the maximum drawdown, we will begin to see a relatively rapid reversal of the water level gradient, as the drawdown, which is hydraulically bound to the ship, moves into the downstream groyne field. We can now see the upstream groyne field beginning to refill with water as we anticipate the arrival of the stern wave. Due to focusing effects, wave energy is highest in the root area. The arrival of the stern wave, working with the drawdown-induced water level gradient, sets up a quasi-stationary, highly turbulent overflow over the groyne, as we can see here. This overflow process begins in the root area and spreads along the groyne body. It is precisely these overflow events that can be highly damaging to the groynes. Now, this video shows a sort of worst-case scenario. The exact nature of the wave structure interaction, as in whether overflow events occur and how severe they are, is highly dependent on the ambient water level, the structure freeboard, and the exact nature of the ship wave and the ship passage. So they don't always occur, or they can occur and not be so severe, but they can also occur and be very severe. Over the last 2 decades, shipborne loads have successively increased in response to increasing vessel dimensions. Ship-induced loads are now the relevant design parameter in large parts of German estuaries. Groynes and training walls in particular are vulnerable to the overflow processes witnessed in the previous video, since they have not been dimensioned to withstand these types of loads. The action of the long-period waves manifests itself in very characteristic damage patterns in estuarine groynes. Typically, a telltale sign is erosion on the lee side of groynes, as we can see here and here. Also, the root area and the crest area are very vulnerable, as can be seen in these pictures from the lower Elbe estuary. Here, the root areas of a whole group of groynes has been obliterated by primary wave action. We are seeing an increase in these types of damages in other parts of the Elbe estuary too. However, due to this exceptionally severe damage at this site in the lower Elbe estuary, the study site for our field experiment is located here. As we can see on this map, the study site of Sand is characterized by close proximity to the navigational channel of the port of Hamburg, thus leading to particularly close passing distances, especially for outgoing ships, and thus high ship-induced loads. The field experiment involved the rebuilding of 2 of the damaged groynes, shown here as B29 and B31. B29 was rebuilt with a wide recess and scour protection in the root area, but no root in the traditional sense. The other B31, which functions as the reference groyne in this study, was built in a conventional design, only that the groyne root was strengthened by widening it and increasing the radius of the root to 25 meters. The recessed groyne design was inspired by the observed damage patterns and aims to reduce wave focusing effects and allow the bypassing of wave energy. Both groynes were rebuilt using the original rock grading of CP 9250 in order to gauge the performance of the geometrical modifications. The field experiment was set up with the aim of monitoring the damage development of both groynes, as well as the hydraulic loads on the groyne body. The deformation of the rock armour was recorded by means of two pile-mounted terrestrial laser scanners, which would scan the respective groyne surfaces at every low water. Hydraulic loads were recorded with pressure sensors at multiple locations around the groyne, shown here as yellow dots. At the recessed groyne, an ADV, indicated by the red dot, was placed on the crest to measure overflow velocities. Wave events were cross-referenced with AIS data, thus allowing loading events to be correlated to ship characteristics and nautical parameters. The net monitoring period was approximately 3 years. In these difference plots, we can see the deformation of the rock armour after 1 3/4 years as derived from the latest scan data. We can also see corresponding photographs giving a visual impression of the damage development in this time period. At the top, we see the deformation of the recessed groyne, in the order of less than about a half a meter on the lee side of the groyne. In comparison, we can see that the reference groyne fared a lot worse, showing complete destruction of the crest area and deformation in excess of a meter. This first appraisal in April 2017 indicated that the new recess design obviously had its merits. However, the damage was still deemed too high. For this reason, in a second phase of the field test, the recessed groyne was reprofiled with a larger rock grading of LMB 540. The reference groyne was not reprofiled. Here we can see a difference plot after 2 years with the larger rock grading, representative of the groyne condition in December 2019. We can only see very small deformations in the order of 10 to 15 centimeters, also on the lee side of the groyne. These can be interpreted as an initial rearranging of the rock armour into a more stable position. The recent photograph from August 2020 shows that the groyne is still very much in a good condition. Looking into the hydraulic performance of the optimized groyne, this figure compares the wave heights measured at the pressure sensor locations around the two groynes. Apart from the histograms, the maximum and medium wave height, as well as the percentage of recorded waves which exceed 1 meter height, are given in the lower part of the figure. First, we can compare the wave height at point 1, at the tip of the groyne, which is largely unaffected by the wave structure interaction. We can see that the maximum and median wave heights are very similar here, within approximately 2 centimeters, indicating that the wave conditions are comparable at both groynes. Comparing positions 4 and 5, we can begin to appreciate the effect of different groyne designs. The conventional groyne shows a strong wave focusing effect, with wave heights increasing towards the root area. The largest wave heights are recorded at position 4. As the wave energy is then redirected over the groyne, we also record higher wave heights on the groyne crest at position 6. In comparison, the recessed groyne shows significantly smaller amounts of waves exceeding 1 meter height in the root area, as the wave energy is allowed to bypass. This also results in lesser wave heights on the crest at position 6. We see that the new design offers better hydraulic performance and lesser loads on the rock armour in the vulnerable areas of root and crest. Maybe some of you are thinking that you would have expected to see a greater quantitative difference considering the significantly larger damage at the conventional groyne. The reason for this is that the statistics are for the entire monitoring period. As the conventional groyne deteriorates, it offers less resistance and the recorded wave heights diminish with time, especially at positions 4 and 5. So in fact, the shown numbers are an underestimation in this case. Taking a quick look at the histogram of measured overflow velocities on the crest of the recessed groyne, we can see that the velocities in downstream direction, indicated here in red, are notably higher than in upstream direction. Discounting turbulence effects, velocities of well over 2 meters per second were measured at the site. These measurements are in agreement with the observation of damages on the lee side of groynes. Unfortunately, no overflow velocities were measured on the conventional groyne, so a quantitative comparison is not possible here. To summarize the finding of our field experiment, we have seen that primary wave heights in excess of 2 to 2.5 meters in the root area and overflow velocities exceeding 2 meters per second could be measured at the site. Whilst the highest wave impact is experienced on the wave-facing side, no damage is typically experienced here. The structural damage to groynes is related to the high velocity turbulent overflow phenomena to which the root, crest, and lee side slope are particularly vulnerable. With the understanding of this particular wave structure interaction, we now have the knowledge to design groyne structures with the aim of reducing the magnitude of these overflow events, as this is the key to increasing the structure lifetime. The recessed groyne design has demonstrated a measurable improvement in armour layer stability. This is achieved by optimizing the wave structure interaction in a way that reduces wave focusing in the root area, permits the wave energy bypassing, thus decreasing overflow loads in the crest and lee slope areas of the groyne. Naturally, rock armour stability can also be increased by simply the use of a larger rock grading. However, to date, no applicable methods exist for the sizing of rock for the observed overflow loads. Also, design modifications can be seen as supplementary measures to avoid the use of excessive rock sizes. So we find that recessed groynes are a practical solution for the increased structural resistance to long-period shipwave loads, particularly in the absence of a design method for the correct rock sizing. The successive rebuilding of groynes at Ulsand in the recessed design is currently being considered. Viewers whose interest has been piqued by this short overview here can find much more detailed information in these following publications. Last but not least, I'd like to thank you very much for your attention.